Hey everyone, I'm Shahab, co-founder and CEO of Lakesail. We're the company behind Sail. So at Lakesail, we understand that compute infrastructure will be the basis for the economy of the future. It's becoming apparently clear with the explosion of AI workloads and agents, right? You know, if you're in the open source community, you've probably seen the explosion of open source contributions the day Opus 4.6 came out. So for those of you who don't know what Sail is a distributed multimodal computation engine. We unify batch processing, stream processing, ad hoc workloads, and AI workloads. We expose support for AI workloads via Python UDFs, which are user-defined functions or can be user-defined aggregate functions or table functions or window functions. And then we also support custom data sources they can read and write to. So if you want to create a Postgres data source or whatever arbitrary data source, you can do that too. So we're going to go over Lakesail's distributed processing architecture. What you're looking at here is the legacy driver architecture, specifically that middle spot where it says worker manager and driver state and driver actor. So it's the actor model with a single threaded event loop. And the question is, why evolve the distributed processing architecture? I think a good analogy is there's no point in having a Ferrari if every time you ride in it, you fly off the cliff, right? And so our goal was to create resilient and observable architecture. So we decomposed the control plane into a worker pool, job scheduler, and task assigner. You still have this actor model with a single threaded event loop powering it all. So the anatomy of a job graph. A job graph is a DAG of stages, and a stage is partitioned, which allows for parallel execution of tasks. The job is the top level unit of work. A stage is a fragment of a physical plan, which has one or more partitions, and then a task processes a single partition. And then tasks have attempts. So if a task fails, it can have multiple attempts, and we'll go through that a little bit more. So slide's a little busy, so we'll break it down. With tasks, you have what's called a task region, which is a set of tasks across stages. So multiple stages can exist in a task region, for retry failure mechanisms. You have the scheduling unit. So within a region, all tasks are scheduled and retried together. And then within a task region, you have pipeline shuffle. So it's local streams for data transfer. And then boundaries between task regions, you have blocking shuffle, which is written to remote object storage. So the first example is what pipeline shuffle looks like. You have an aggregation of 4 partitions, a join with 8 partitions, and then you're repartitioning from 4 to 8. So with pipeline shuffle, you have one task region. You can see all tasks are in the same region, and they can all be processed sequentially. With blocking shuffle, the gold outlines different regions. So you have 12 regions, and the next region is dependent on the previous region. So how does task law and resource management work? You can think of a task law as a logical representation of what a task is allowed to do and what it's allowed to have in terms of CPU and memory. And they get to share slots. So you can pack a bunch of tasks into a slot so you can be really efficient with your resources. Within a slot, tasks must be from different stages, because if they're in the same stage, then they're dependent on each other. And so if you have a task from stage 1 and stage 2, they can exist in the same slot. But if you have 2 tasks from stage 1, they can't exist in the same slot. So DataFusion powers all of this, and how we do that is via distributed query planning. So if you contributed to DataFusion or you use DataFusion, you're probably familiar with the execution plan. And the goal is to break down the execution plan into distributed stages to form that DAG. The producer wraps the input in a shuffle write exec. The consumer ensures the execute still works when the input is replaced by shuffle read exec. So now what's really cool about this is you have task definitions decoupled from physical plan rewriting. So the control plane, the driver, right, can be focused on scheduling, and the task runner, which is on the worker, can rewrite as needed. So let's look at the input modes. For coalesce and repartition, the input mode is shuffle. For system table exec, which powers our internal system catalog, that's forward. And then for cross join, hash join, nested loop, and piecewise merge join, it's going to be broadcast and shuffle. And then lastly, for preserving merge and exec, that'll be merge. So shuffle, it's output partition P, fetches channel P from input partition. Forward, it's the driver directly passes to the worker only if needed, and that's only used from the system catalog. And then broadcast, it's every partition fetches all the input. And then merge, single output partitions fetches all the input partitions. So for future work, data plane for blocking shuffle. Right now it's streaming shuffle, but we will soon support object storage based data plane for blocking shuffle so that you can spill to object storage rather than spill to local disk. And then configurable slot sharing groups. Right now you can't configure slot sharing groups, but soon we'll add configuration options and heuristics to customize slot sharing behavior based on workload characteristics. And then previously we talked about the various input modes. The goal is to support a broader distributed broader patterns for distributed execution. Next, we're going to talk about how Sail supports lakehouse formats. So in a traditional listing table, you have data files to read and via directory layout. After writing, you don't do anything. And then any sort of complex DML operation isn't really supported. You have to do a full table rewrite. Statistics are generally inside the data files, such as Parquet. Schema is inferred from the data files largely, and partitioning is also inferred from the directory layout largely. Writer conflicts aren't supported. Lakehouse tables, they really operate via manifest files, right? So tons of metadata. Data file, you read the manifest file. After writing, you update the manifest file. And then for any sort of complex DML operation, those are supported. They should be efficient in theory. And then statistics are decoupled from the data files. They're stored in manifest files. Same with schema. Schema is not inferred. It's stored in the manifest, versioned. Partitioning, manifest. Writer complex, manifest. And so this manifest file becomes really, really important. And you soon learn that the metadata becomes data, which is a problem for computation engines. With Sail, we decided to fully start building the Delta Lake and Iceberg specs internally. The reason for doing that is we discovered that it really requires deep integration with the engine. When you understand how involved the spec becomes. With Delta Lake, we support everything, for reading and writing. We support conditional deletes, and we support merge operations. Updates will be supported soon. Iceberg, we're lacking a little behind. We support read and write. Delete and merge will come soon as well. And we decided to support merge operations before update operations because merge operations involve updates and deletes, and so we wanted to inform our architecture by doing the harder one first. And so with Delta Lake, our journey was Delta RS and Delta kernel. We then understood the full Delta Lake spec, decided to go Delta kernel RS only, and then now we're writing the full Delta Lake spec for physical plans for DML. Soon we'll have a distributed Delta log scan. So let's go through how a merge operation works. It's the most complex DML operation, and we tackled it first to help inform future architecture decisions. If you look at the merge statement there, right, you have an update, you have a delete, you have an insert. And so you have to remove all files touched by on the on and match conditions, write new files for update and insert results, and then write manifest at the end for added and removed files, which is very involved. If you look at the query planning of what this ends up being, you have some sort of input protobuf message that could be Spark Connect or SQL, AST. We convert that into an internal representation of the sales spec, which then eventually gets converted into some sort of DataFusion spec, which we build logical physical plan and custom optimizer rules for. So the ones we defined were merge into nodes, which is expanded by the logical plan and rewritten by the optimizer rule. And then we build the initial physical plan and optimize that physical plan. This is a very simplified kind of diagram of how merge works. And you can see where the delta commit exec has this union of metadata, and it has to delete, has to write, has to update, and has to insert rows. So it gets very involved very quickly. The key takeaways that we learned from deciding to build native Delta Lake and Iceberg support internally was that metadata is data and scalable processing is really required. There's so much overlap between Delta Lake and Iceberg that we started designing a path for modular plan nodes where these logical and physical plan nodes should really be composable and flexible across various operations. And optimizer integrations are really important for metadata and data file printing. Future work, distributed DML, testing and benchmarks. So making sure our integration works at scale, building those reusable plan nodes as we previously talked, and then we actually found a path for shared DAG nodes, and where you can avoid repeated execution of common data and metadata scans. And so turning that tree into a DAG, just like how we turned the job, the job top level unit of a query into a job graph, which is a DAG of stages. And then the last piece of sales architecture is the catalog interface. So we have we use the catalog provider trait. It's a flat structure. It's a single trait for databases, tables, and views. And then it has an async interface so that you can integrate with external systems like cloud catalogs. It's really focused on cataloging objects, and we don't do any query planning inside of it. This is a distinct difference than DataFusion's catalog. So DataFusion's catalog is hierarchical. It doesn't have an async interface, and that's intentional, right? Performance is really critical in DataFusion's catalog, and the responsibility are the catalog objects plus query planning. The implementation effort there is high, and for a good reason, you get that extra performance. For Sail, it was important to have easy integrations with external systems, which is why we implemented this catalog interface so that we can have that async interface. And one thing that we found missing from data engines was a system catalog. So if you've worked with Postgres or MySQL or really any database, you've probably gotten pretty familiar with the system catalog, which helps you debug stuff and learn what your workloads inside the database are doing. So we rolled out a system catalog for Sail, which is supported via OpenTelemetry and gives you observability through SQL. And so you can actually query information about sessions, jobs, stages, tasks, and workers. And we actually use this system catalog while developing our new distributed processing architecture. It was really, really helpful. So how does it work? It uses Sail's catalog provider. It's a table schema with a temporary view, and we rewrite it as a logical plan extension, and we actually execute it as a execution plan during physical planning. Future work, side effect free planning. So we want to make sure query planning is free from side effects. That means removing all of the catalog operations to physical execution rather than the logical planning stage. And in DataFusion, catalog operations are also at the logical planning stage. Make explain output more intuitive by including all the catalog operations, and also supporting catalog operations after DML. so you can update manifest locations after a lakehouse commit, for example. Is that it? That was it. Thank you, everyone.